Okay, so after plugging all that in your calculator and getting all these answers, let me put up my answers real quick and we'll talk about that.
It just looks like a lot of squiggly lines.
There are a lot of squiggly lines on the page, that's for sure. Okay, so
I'm sorry, I just get out of athletics and run a lot in this heat.
it's okay. But then they turn the air on in here and it gets cold real fast. Okay, so they do the example. Then there's number one. Remember, to find degree, you just have to look at the equation. You don't have anything to do with plugging in the calculator. Number one has a degree of 2. There's the graph. Looks kind of like that. Has just one bend, and both the left end behavior and the right end behavior end up. Then there's number 2. It has a degree of 1 because there is no exponent on this x, but when there's not one, there's a 1. So it has the highest degree is 1. It's a line, has no bends, and the left end behavior is up, right end behavior is down. The next one is high degree of 3. It has 2 bends, left end behavior down, right end behavior up. Number 4, degree of 3, 2 bends, left end behavior up, right end behavior down. Next one has a degree of 3 as well. Also has 2 bends, left end behavior down, right end behavior up. Next one has a degree of 4, 3 bends, both left and right end up. Number 7 also has a degree of 4, 3 bends, both end down. Number 8 has a degree of 5, 4 bends, left behaviors down, right behaviors up. Number 9 has a degree of 6 with 5 bends, both behaviors end down. Alright, so the real question is, did you start to identify any type of pattern in what was happening here? Specifically, it asks at the top of page 3, what is the general relationship between the degree and the number of bends?
I was going to say something.
Look back at them and see.
So there's going to be one less bend than degree.
Very good. There's one less bend than the degree. So the number of bends so then it asks in number 11, how does the degree of the polynomial affect the end behavior? This one's not quite as straightforward to see, so they gave you a little hint. Compare even and odd degrees and see if that helps you come up with something. So look at all the ones that have an even degree, 2, 4, 6. What do you notice about their end behavior versus those that have odd, 3, 5, 7? 1, 3, 5, 7.
Well, the ones with the even degrees have 2 bottom or 2 top.
Very good. Very good. If the degree is even, the ends always end in the same place, either both up or both down. Whereas if they're odd, you always have one up, one down. And we'll talk in just a minute about how you can tell which one's which, but if the degrees are even, now, before we move to the next thing, I want to make sure you make note of something that you've actually already known about. See, we spent an entire, probably month, studying a very specific even degreed function. What even degreed function did we study? A lot. We spent a long time on it. It has its own formula that has a song that goes with it.
The quadratic formula.
Right. A quadratic. What degree is a quadratic?
2, that was the word.
Yeah. Squared, right?
Yeah,
It's squared. It has a degree of 2. That's even. And it ends like this, yes? Always. Both ends are up. All even polynomials, 2, 4, 6, 8, 10, if they have a degree that is even, they are going to end their behavior just like a quadratic. So if in your mind you can remember what a quadratic does, all even polynomials will follow that. They'll just have more bins in between. You spent an entire year in the 9th grade studying one particular function that has an odd degree. What function did you spend your entire year? Linear. What's the degree of a linear function? 1, right? It's a linear function is to the first degree. That's odd. And the linear pair function looks like this. 1 up, 1 down. So all odd functions, 1, 3, 5, 7, 9, etc., they end their behavior just like the linear function does. So if you can remember how a linear function behaves, then you can remember how all the odd functions behave. Only difference is there's going to be extra bins in the middle. That's it. So in this particular unit, we're kind of studying all polynomials because they all are very similar to each other. And you'll see in the next day or two the main differences, but the behavior is very similar. So with that in mind, it says look at the right end behavior of each function. What about the function determines whether or not the graph will point up or down? What about a quadratic function determines whether or not it points up or down? When does it point down? When it's negative. That's it. If the lead coefficient is negative, it goes this way. Think about the linear pair function. It goes like this. What would make it switch and go like this? Yeah, negative. If you make it negative. So it's the same. If I have a cubic function, which looks like this, looks like a little guy, like this, the only thing that's going to make it switch its behavior from this, which is just like the linear pair function, by the way, just bin, is if you make it negative. And if you make it negative, it switches, just like the linear function switches when you make it negative. So that's what changes the end behavior to being down. If it has a negative lead coefficient. It's important that we say that it's a negative lead coefficient because there can be numbers in between there, and you'll see in just a minute when we actually define a polynomial, that there can be numbers in between there and they can be negative. It's just that one at the beginning of that from a quadratic though. Just the one in the front. If it's negative, that's what flips the whole thing over. Okay, so real quick, I'm going to have you look at 13, 14, and 15. I'm not going to tell you. You just decide by looking what degree it is and whether or not it has a positive or negative lead coefficient. I'll give you a minute. Give me a minute. 13. What degree is it?
5.
It's 5. Now, before I even counted bins, I knew it was odd because it has 1 up, 1 down. So it has to be odd. So then I just count the bins. There's 4. So that means it's degree of 5 is a positive or negative lead coefficient. Positive, because it's just like linear parent function. And it's just like that. Next one. What's the degree?
It's
7. 7th degree. Again, I knew it was odd because it's got 1 up, 1 down. It's 7th degree. This time, what's your coefficient? Negative. Because the linear parent function would end like this, and that one's backwards. It ends like this. So that means it has to be negative. It's upside down. This one I can tell both in the same place. So it's got to be even. 1, 2, 3, 4, 5, 6, 7 bumps, which means this is an 8th degree polynomial, and negative lead coefficient because they both end down. Everybody good? Easy, right? You know, it actually, I mean, this is pretty much it. Here's the good news. Think about how much you know. Think about how much we've learned. We spent so long on quadratics that the rest of this should be easy because polynomials all pretty much have the same behaviors. So since we know how quadratic works, we pretty much know how all the polynomials.
You did already?
Yeah, I did.
Oh,
First off, we forgot.
How there is though. Now let me before I give you all this. Let me say there is one little caveat where the counting of bins is concerned. Sometimes there are you can't see the bins, much like imaginary zeros. There is a situation where you can't necessarily see the bins to count them. I would never give you one of those on a test and say, hey, what degree is this? And then trick you and be like, hey, there's 6 bins, but you only could see 1. I wouldn't do that. If I'm going to have you count bins, I would make sure it's one that you can actually count them. But you're about to see this. When you plug it, before I even say it, how many bins should x cubed have? Should have 2 bins, right? Well, when you plug x cubed, the first x cubed into your calculator, which by the way is the cubic parent function. Hold on, let me switch this. Okay, when I plug x cubed into my calculator, it's not all that clear on this one that there are 2 bins. There really are, but there's this one and there's this one, but it's not quite as clear as on the next one. When I plug in, I'm going to put them both in there at the same time. If I put x cubed real clear. You can see it. So, but just so you know, I would never give you one like the parent, except for the fact that you know what the parent function is. I would never give you one like this and say, hey, count the bins for me, because that's kind of unfair. But I would give you one more like this red one, where the bins are very clear. Okay, so I want you to graph A, B, and C, and then we're going to list some similarities and differences, and you're going to do that for this whole page. Now, when I say similarities and differences, let me tell you the things you're looking for. Things like x-intercepts and y-intercepts, if those happen to be the same. Things like end behavior, if the end behavior changes, and stuff like shape. Like clearly, the A and B do not have the same shape. But when I put C in, it has the exact same shape as B, it's just reflected. Okay, so you can say A and B definitely have the same y-intercept. They don't have the same x-intercept, but they have the same y-intercept. And they have a different shape, but when I put C in, I can say B and C have the same shape. C is just a reflection. So I'm going to give you a few minutes to graph it. And again, do not worry about your sketches being perfect. They do not have to be. Just sketch them.
10.
Because mine's.
Yeah, switch it to -10, 10.
Okay.
Because you won't be able to see it. That window, yeah, switch it.
Okay. Because I was like, hers is smaller than mine, so I was like.
Yeah, switch it, because there's, I for sure said that's right.
So negative and.
-10 and 10 on both X and Y.
Man, I was
Oh, I like that one. Harry Potter.
Yeah, you know how many states are here? Boom. I just want to do all of them. Animal protection area is there's the protection over there. First off, there's sides of the wall inside. There's like the way I put it, the way she's holding it, there's two big holes in each stomach. There'd be a fire, like she's like, oh no. She'd be in a burning house. She's like, oh, I know what to do, guys. And so like that is smoke invasion.
You gotta match them. This looks fun. They said you have to know the number. Yeah, there's a missing number. Each function is incomplete because not all the terms of the equations are listed. However, enough information is provided to match these functions derived by the
Let's
letters.
just think about it. There's 1, 2, 3, 4. 4 bumps, so that means it's gonna be.
4 bumps.
Yeah, 4 bumps.
I have all three of them.
There's gonna be a third
For
degree.
what, number 2?
It has to be the.
It's positive, so it's this one.
2 bins. 3 bins.
But it was another one with 2 bumps, like this one. 1, 2, 3. Oh, 1, 2, 3, 4. And then you go to the little. Yeah, because there's
See?
the number of bins is one that's in the degree. Bins is the degree.
I only see one.
Right? Was I right?
Do what?
Yeah, I was right. The degree is higher than the bins. 1 higher.
Yes.
I gotta write that on here.
Oh, shoot, wait. This one's cheap. Because there's 1, 2, 3, 4.
There's only 3 left.
And there's, the degree is higher, so it's not.
What about E? E is 5.
It's negative.
Ah.
I get this. I understand.
I was like,
It's
wait a
pretty
minute.
simple.
I really
So
like.
what are you writing on here? Just positive?
That's what I did it so I could like, so it can help me.
Are you starting it from?
Like this one's negative because it's
It starts with negative?
Yeah. and this
Negative.
one's positive. It says negative.
Wait.
But this one ends in negative.
Oh, so you're going where it ends at? Okay. Wow. Dude. Smell how good this stuff is.
Okay, let me give you the definition, top of page 2, it says, for you to describe or define what a polynomial function is. Well, you wouldn't necessarily have any way of knowing that on your own. I mean, you could probably come up with some things that it definitely needs to have, but I don't know that you would necessarily come up with the definition all by yourself if I didn't give it to you. So I am going to give it to you. Definition of polynomial function.
Give it to me.
It is a function exponents on a polynomial function must be positive whole numbers. Now, if you think about this, it actually makes perfect sense. Think about the polynomial functions that we just talked about. Linear functions are polynomials, and quadratics and cubics. Those are all polynomial functions. To the third degree, over here, is called a cubic. Notice the name of a fourth degree polynomial function. It's called quartic, a quartic function. If it's to the fifth degree, I'm not sure why they didn't write this one in. These are called quintic. And actually, if you look on your calculator, if we were to put data in our calculator, I don't know if it'll let me just show you or not, but we'll see. Yeah, if you look here, my calculator has the ability to not only do linear regressions like we were doing the other day, but it can do quadratic, cubic, and quartic regressions as well. It can come up with cubic functions and quartic functions also. It doesn't do quintic functions. I'm not sure why. Maybe, I don't know. It just doesn't. But quintic is fine. After quintic, we just start calling them 6th degree and 7th degree and 8th degree. They don't have special names after that. But they're always positive whole numbers. Now, if you think about it, it makes sense because what if I had this? X, let's say y equals x to the negative 1. What is x to the negative 1? Can I write that like that?
No.
What do I have to do?
You have to bring the exponent down to
What? I do. So it would be like this.
Yes.
And what function is that?
Log, no,
Uh-oh.
give me a minute. Rational.
It's the rational function. Can anybody tell me off the top of their head what it looks like?
It's like this and this.
Yeah, like this and this, right? It's got the two pieces with the asymptote in the middle. So that's what happens if you have a negative exponent. It becomes rational because it puts the x in the denominator. Because this means you have to move them downstairs. So that's not a polynomial function. And the other one we've also done, because what if I had this? Y equals x to the 1/2 power.
Ooh.
What is that?
That is. Oh shoot! Hold on.
You're gonna have to take this one.
Would it be radical?
It would be radical because this is the same thing. Remember, the bottom number goes in the crack.
Yeah,
This is the same thing as that.
It's also called square root.
Yeah, it's a square root function, and we've already done that one. You remember what it looks like? Right?
Yeah.
Dot
yeah.
and arrow. It's not a polynomial function. Polynomial functions have to have positive whole number exponents. So if you are identifying them by function, and for example, on the SAT, I've actually seen this in SAT practice questions. They'll list a problem and they'll ask, is this a polynomial function, a radical function, a rational function? You have to be able to identify it. If you're trying to identify a polynomial function, you just look through there and make sure all the exponents are positive whole numbers. If they're positive whole numbers, it's a polynomial. If they're not positive whole numbers, then it's something else. The other thing that you need to look for when you're identifying whether or not they are a polynomial function is, I'll put this part in parentheses, there can be no x's in denominators under radicals or in exponents. No. If the x's show up in any of those places, they are something else. They are not polynomials. So I'm going to give you the polynomial form, and then I'll give you an example. Because when I write down what the polynomial form looks like, it's very overwhelming, but it's not. So let's see.
find it, or?
It's a to the n,
Oh,
x to the n,
Wait,
plus a to the n minus 1, x to the n minus 1.
we have to write all that down.
Yeah, that's just polynomial form. Now let me give you an example of a polynomial that's in polynomial form.
Wait, what's that?
the top is the same as the bottom.
Okay.
So the n minus 1, n minus 1.
Okay.
Let's do that first. Get it right. And sources. And it just goes on and on and on.
And it just goes on however long it has to go on before you have no more exponents. So, for example, it would be something like this, 4x to the 6.
I didn't even have room.
It goes without that.
That's a polynomial. And all that's happening here is your exponents are going down. In my polynomial function, they go down by 1. But right here, this one went from 6 to 3. That's okay. You don't always have one of every degree. Just because this is a 6th degree polynomial doesn't mean I have a 5th degree place and a 4th degree place. I just skipped them. That's fine. So it just counts down, and you have different coefficients for every degree place. It doesn't really matter. Polynomials can be really, really long, or I could say f of x equals 7x to the 9th. And that's a polynomial. Even though it's just one term, as long as it has a positive whole number exponent, it's a polynomial. It's a polynomial function. Okay, so now they ask us to categorize these statements about polynomials as always true, sometimes true, or never true. The lead coefficient of the polynomial function determines the right end behavior of its graph.
I don't think we were triple.
Well, yes, because it determines whether it's negative or positive.
Okay, is it always true? Sometimes true,
Yeah.
or never true?
No, always, because, like, it just flips. It just determines it.
I agree. It's always true.
A, L, W, A, Y, S, true.
I rolled today. It's so good.
Why is my handwriting
Talking to me.
ugly?
It doesn't matter if it's a even function, if it has an even degree, or if it has an odd degree, doesn't matter. That lead coefficient tells you whether or not that right side is rising or falling. It tells you whether the left side is rising or falling also. All right, what about the next one? If a polynomial function is of an even degree, then its left and right end behaviors will point in the same y direction.
Yes,
Always, sometimes, or never?
always.
Always true. I don't think I need to explain that. If a polynomial function is of a degree n, that means any degree, then the graph will have n minus 1 relative maximum min-mins, or